Hello from wherever you are. I'm hoping you're keeping yourself safe. Our intention today is to discuss or to continue with the discussion of the compounds of period 3 elements. This time around we shall discuss the hydrides. In our previous video we discussed the chlorides. Of course we are still continuing with period 3 elements, the series which includes sodium through up to argon. Of course, in our discussions, we shall center from sodium, or we shall put emphasis on sodium up to chlorine. We shall not talk a lot about argon. The reason is because argon is generally inert. So we shall not put a lot of emphasis on it. So what shall we be looking at? Our emphasis will be on these three. We shall discuss the preparation of the hydrides. We shall discuss the structure and the bonding in the hydrides of these period 3 elements. And then, lastly but not least, we shall describe or discuss the reactions of the period 3 hydrides, or the hydrides of period 3 elements with water. So those are the three things that we shall put emphasis on. To begin, let us see how these hydrides are prepared. Sodium hydride and magnesium hydride are prepared in the same way, by direct combination. What do? The element is heated with dry hydrogen. For sodium, we shall form sodium hydride. For magnesium, we shall form magnesium hydride. It's very important for us to know the conditions for the reaction. Of course, we have said heating is required, and then the gas should be dry. So those are the two conditions for these reactions to occur. For aluminium, unlike for sodium and magnesium, it can't be prepared that way. How is it prepared? Aluminium hydride is prepared by the reaction between lithium hydride and excess aluminium chloride in a solution of ether. So here I will describe that reaction. Lithium hydride reacting with aluminium chloride to form aluminium hydride and lithium chloride. So that's how we prepare our aluminium hydride, because our focus is on the preparation of aluminium hydride. To proceed, the hydride of silicon, which we call silicon 4 hydride or silane or silicon, for it is formed by the reduction of silicon tetrachloride using a very common reducing agent which we call lithium aluminium tetrahydride, still in dry ether. So in this reaction we describe that lithium aluminium tetrahydride reacts with silicon 4 chloride to give us silane, lithium chloride and aluminium chloride as the other products. Of course, notice silicon 4 hydride is a gas, but that's not the only way how silane can be prepared. It can also be prepared by reacting magnesium silicide with dilute hydrochloric acid. It's very important for us not to ignore the reactions of the conditions of reaction. Warming is required and the acid is supposed to be dilute. So magnesium silicide reacts with dilute hydrochloric acid to give us our silane and magnesium chloride as the other product. Notice, magnesium silicide or not, magnesium silicide is prepared by reacting magnesium with the silicon, directly heating a mixture of magnesium and silicon. So that's how we prepare our silane, in a reaction between magnesium silicide and dilute hydrochloric acid. Phosphine, which is the hydride of phosphorus, of course we have seen this reaction before, is prepared by reacting white phosphorus with sodium hydroxide. The sodium hydroxide must be hot, or heating is required, and then the sodium hydroxide should also be concentrated. Of course, we have seen this reaction when we are discussing the reactions of period 3 elements with alkalis. Yes, that very reaction can also be used to prepare phosphine. Phosphine is the hydride of phosphorus. So that is how we prepare phosphine. Proceed. Hydrogen sulphide, which is the hydride of sulfur, how is it prepared? It's prepared by reacting either dilute hydrochloric acid or dilute sulphuric acid with the black solid of iron 2 sulfide. We are able to produce hydrogen sulphide, which is a gas. Hydrogen sulphide is a very pungent gas. So these equations here demonstrate how hydrogen sulphide can be prepared. Of course, down here we have an ionic equation of how this reaction can be carried out. Lastly but not least is the production of hydrogen chloride. Hydrogen chloride is the hydride of chlorine. How is it prepared? It's prepared by reacting concentrated sulphuric acid with either sodium chloride or potassium chloride. All of them are in solid form. So that's how we prepare hydrogen chloride. It's important for us to note, unlike hydrogen chloride, the other hydrides of group 7 elements can't be prepared in this way. What do I mean? Hydrogen bromide and hydrogen iodide can't be prepared this way because for them they are much more reducing agents, or they are much stronger reducing agents than hydrogen chloride. So the products we obtain are bromine and iodine. So we can't use these methods. The details of how those will be discussed, we shall talk about them when we go to the chemistry of group 7 elements. So here we have a summary of some of the hydrides and their properties. We can see we have the elements, sodium through up to chlorine. Then for sodium, the hydride is sodium hydride. For magnesium, it is magnesium hydride. For aluminium, it is aluminium hydride. For silicon, it is silicon 4 hydride or silane, or what we also call the silicon. For phosphorus, it is phosphine. And for sulfur, it is hydrogen sulphide. Whereas for chlorine, it is hydrogen chloride. Let us take a look at the physical properties or the physical states at room temperature. We note that the hydride of sodium, magnesium, and aluminium are all solids, whereas the balance, or the others, that are silicon, phosphorus, sulfur, and chlorine, for them they are gases. Now, the state at room temperature is determined, of course, by the bonding. We note sodium and magnesium are ionic. Aluminium is mainly covalent, of course with some ionic character. We shall explain why it is mainly covalent. Then for silicon, phosphorus, and sulfur, they are covalent. Chlorine, its hydride, which is hydrogen chloride, is also covalent, but it is polar. This is as a result of hydrogen and chlorine having differences in electronegativities, resulting in a biased distribution of the electrons within the bond. So that's why we are saying it is polar. Okay, let us look at the structure. For sodium and magnesium, their hydrides are J and ionic. Aluminium hydride is polymeric, just like aluminium chloride, and the others, that is silicon 4 hydride, phosphine, hydrogen sulfide, and hydrogen chloride, are simple molecular. Let us discuss this structure and bonding. We are saying that as we move from sodium through up to chlorine along period 3, the elements become less electropositive. So once they become less electropositive, the tendency to form ionic hydrides reduces. So they become less electropositive, meaning they become more electronegative. So there is a higher tendency to form less ionic hydrides and a higher tendency to form more covalent hydrides. So that is what we notice in that trend. So for that reason, sodium hydride and magnesium hydride are ionic. Aluminium hydride is expected to be ionic, but it's not. It's mainly covalent. Why? Because everything comes or arises from the behavior of the aluminium cation. It has a small ionic radius and a big charge. Having a small ionic radius and a big charge gives it a high charge density, which results in also a very high polarizing power. So having high polarizing power, this we have discussed previously, is a recipe for formation of covalent compounds. So for that reason, although aluminium hydride is expected to be ionic, it's mainly covalent because of the properties of the cation of aluminium, which is small in terms of size, or has a small ionic radius and has a very big charge. As a result of that, it has a high charge density and a high polarizing power. The hydrides of silicon, phosphorus, sulfur, and chlorine are purely covalent, and as a result of the differences in the bonding within these hydrides, we shall notice that even the melting points are affected. For example,
Hydrides which have ionic bonding have higher melting points compared to hydrides which have covalent bonding. Let us look at the last part of what we intend to discuss, and that is the reactions of these hydrides with water. We notice that sodium hydride reacts with water to form sodium hydroxide and hydrogen gas. The same thing will happen with magnesium hydride and aluminium hydride. Silane, however, it's not readily hydrolyzed. It will be hydrolyzed in alkaline medium. Why is this so? The reason is silane is a symmetrical molecule which is tetrahedral with a bonding angle of around 109.5. So as a result of that, this reaction is difficult. So to facilitate the reaction to occur, we provide alkaline conditions. And then what happens? Silane reacts with water in alkaline medium to give us silicate ions and hydrogen gas. Phosphine does not react with water because it's non-polar, meaning it does not dissolve in water. So here the reason does not arise from the geometry of the molecule like in silane, but here the problem arises from the fact that phosphorus and hydrogen almost have the same electronegativities. Phosphorus, for example, according to the Pauling scale, has an electronegativity value of 2.19, whereas hydrogen has an electronegativity value of 2.20. So you notice that 2.19 and 2.20 are almost the same values. So for that reason, the electronegativity being the same, that means the bonds are non-polar, and if the bonds are non-polar, then the whole molecule ends up being non-polar. Hydrogen sulphide, on the other hand, for it to dissolve in water to form a weakly acidic solution. In these reactions, we describe how the hydrogen sulphide dissolves in water to form weakly acidic solutions. Hydrogen chloride, for it reacts with water to form hydrochloric acid. So that's why we are saying that the solution is strongly acidic. So I want us to notice one trend in the reactivity of these hydrides or period 3 elements with water. We notice that sodium hydride, magnesium hydride, and aluminium hydride form alkaline solutions when they react with water. The hydrides which are in the middle have a lower tendency to react with water. We have explained, for example, silicon 4 hydride and phosphine. However, as we move to the extreme right of the period 3, the hydrides of those elements, that is sulfur and chlorine, they form acidic solutions. So that means there is a tendency for the elements to form there's a tendency for the hydrides to become more acidic as I move from sodium hydride towards hydrogen chloride. So that is what I wanted us to notice there. So that is what we intended to discuss. First of all, I wanted us to discuss the preparation of these hydrides of period 3 elements. That's the first one. 2, to describe the structure and bonding. And then lastly, to discuss or describe the reactions of these hydrides with water. I'm hoping you can be able to do that. And in case you have any issues, you can always send me a mail. I'll be able to respond, or you can text. I'll be able to see your question. For more resources, you can check out these websites. Thank you so much for attending, and stay safe.